Okay, good afternoon, folks. We have the career fair going on today, so we don't have as many students in class, so in case you're wondering why that is. But still, I have the sign-up sheet. It's circulating around. So we are going to continue our discussion about realizing switches. Last time we talked about the available semiconductor devices, such as diodes, power MOSFETs, and IGBTs, and their characteristics and what quadrant they are covering. Then, as an example, we looked at a buck converter and how the switches are realized. So, for instance, what we saw last time was if you are trying to realize a buck converter like this. We looked at the switch realization and realized the top throw switch could be realized like an IGBT or a MOSFET, and the bottom one is basically a diode. So what we did last time was we looked at the voltage drop of each individual single pole, single throw switch, and also the current that is passing through that switch. Then we looked at the available products that we have, which are diodes and IGBTs and MOSFETs, and realized that the top throw switch is an active switch, like for instance, MOSFET or an IGBT, and the bottom one is a diode, which is a second quadrant switch. Now, as we have seen in the paper that we studied I think it was last week, in power electronic converters, most of the time switches appear in pairs and they actually form a single pole double throw switch. So one approach would be, instead of trying to realize each one of these switches individually, we can actually identify the pairs and directly just realize the pair. So that's what I'm going to be talking today. Now, before getting into the discussion, I have to make a bunch of definitions, and this is the standard single pole double throw switch that I'm going to be using. All right. Now I'm going to assume that the pole current is flowing from left to right. I call it I sub P. So if the current is from left to right, it's actually a positive current. And labeling this one to be throw number 1 and then this one to be throw number 2, I am actually labeling this voltage, throw number 1 voltage, with respect to throw number 2 voltage, to be V throw voltage, basically. All right, something like that. And I'm always drawing my throws on the left side and the pole on the right side. And obviously there is a control applied here, a control signal. Let's call it C. And again, the definition is if C equals 1 or active or true or 5 volts or something like this, the top throw is engaged. And if C is 0, the indication is that the bottom throw is engaged. So this is my kind of basically definition. So the pole current, I pole, so let me write it over here. IP is the pole current. And VT, which is the voltage of throw number 1 minus the voltage of throw number 2, is the throw voltage. Okay. So this is the classic definition. Just keep this picture in mind. And now, looking at the Bach topology over here, we could argue that the throw voltage is positive, and the pole current is also positive. And then this was the realization. All right? So the question is, do we have other quadrants that actually we can realize a single pole double throw switch. So if I want to draw the diagram, we are looking at a diagram like this. So let's say we have the pole current drawn versus the throw voltage. And if they are both positive, that means we are in the first quadrant. And our example was the buck converter. And our switch realization was something like this. Okay. Okay, something like this. And by the way, the control was applied to the switch. So if the control is active or on, that transistor is on, and actually the top throw is engaged. Now you may think about, there might be an application that, for instance, our throw voltage is positive, but the pole current is negative. So basically we are trying to cover this quadrant. And I'm just going to have an example for this. How are we going to realize that switching requirement? So let me draw it here and then explain it. So this would be the switch realization for that application. Okay, so if the pole current is negative and we want the bottom throw to be active, basically we have to turn the switch on. Then the current is going to flow in this direction. And if we keep the switch off, because the pole current is negative, it is going to actually push the diode to be on, so it's going to flow in this direction. So depending on which one of the throws we want them to be active, we can turn the transistor on or just keep it off. So if the transistor is on or C is 1, you can see the bottom throw is active. That's why I'm actually writing 1 minus C down there, and the diode is actually up there. So remember, C is always indicating that the bottom throw, the top throw is active. So right now, if C is 1, transistor is off, therefore the top throw, which is the diode, is going to be conducting. So this is the switch realization when your throw voltage is positive, but your pole current is negative. So do we have an example for this case? Absolutely we do. And that is actually the boost converter. I'm just going to explain it. Okay, so this is when C equals to 0. And this is when C equals to 1. All right, so let's look at the boost converter. So remember, right now we're assuming that the pole is on the right-hand side, the throws are on the left-hand side. So if I want to draw the boost converter, it is going to look like this. And again, I assume that I pole is positive if it is flowing from left to right. So this is actually my boost converter. But if you want to get power from the battery and actually send it to the load, this turns out to be a negative current. So technically, we are looking at a single pole double throw switch with the output voltage is positive. So VT is positive. I pole is negative. Therefore, we are looking at a fourth quadrant switch and actually a realization for the boost converter. So if you want to realize the boost converter from what I drew earlier, this is how you're going to realize it. All right, so something like this one. So immediately, if you see the structure of the boost converter, you can use this, four-quadrant diagram and decide, okay, it's the fourth quadrant, therefore the switch realization, we have a diode on top and we have a transistor in the bottom. Now, there might be a case like if you are operating in the second quadrant where the pole current is positive, but the throw voltage is negative. So what would be the switch realization for that single pole double throw switch? So all you got to do is basically you got to swap the position of the diode and the transistor. All right. So you can see that they can block negative voltages. Like if the transistor is on, the diode can block that negative voltage, no problem. If the diode is conducting, the transistor is actually capable of blocking that voltage. And at the same time, conduction of the pole current is not a problem. If C is 1, the current is going to flow in this direction. C is 1 means 1 minus C is 0, therefore the transistor is off. So the only way for this current to flow is just to flow through the diode, and therefore the top throw is engaged. And if C is 0, the conduction is going to be from here. Because then the transistor is on, the diode is reverse biased, and the current is flowing through the transistor. So this is in case you are operating in the second quadrant, your pole current is positive, but your throw voltage is negative. What about the third quadrant when they are both negative? So this is going to be your switch realization. Oops. So compared to the diagram above, the second quadrant, I just swapped the place of the diode and the transistor. So because all I did, I just displaced them in terms of voltage, we don't have a problem. We can still assume that if one of these components is on, the other one can block the voltage, which is a negative voltage. And if C equals to 1, the current is going to flow in this direction. And if C is 0 or off, the transistor is off. Therefore, the current is going to force this diode to turn on and flow in basically this direction. Okay? So this is like the realization of a single pole double throw switch, looking at all the quadrants. So when you are analyzing a converter, like the converters that the cells that we saw on that paper, you have to identify the single pole double throw switches, then see what is the direction of the pole current, what is the polarity of the throw voltage, and then take that ideal switches off, those ideal switches off, and replace them with the appropriate, basically, quadrant. All right. So you may ask, there might be a case where basically the throw voltage is, like in a bidirectional power application, the throw voltage is positive, but the pole current could be positive or negative or basically bidirectional. So in that case, what would be the realization of the switch? So we are kind of talking about combining the first quadrant and the fourth quadrant. So what we do is actually we take the component that we have for the first quadrant and kind of put them in parallel with the components that we have for the fourth quadrant. So let me draw it over here. So this is in case if, for instance, let me draw it first and then explain it. I'm just going to draw this very short, and basically this is going to be the realization. So this is what we had for the first quadrant, and I'm just going to place it in parallel with what we had for the fourth quadrant. Okay, so we don't know. The pole current could be positive, it could be negative. If the pole current is positive and we want it to flow through throw number 1, this would be the basically direction. This would be the path for the current to flow. If it is still positive and we want this bottom throw to be on, we just turn that transistor off, and then this would be the path for the conduction of the current. So these are for positive currents, and if the currents are negative, if you want the bottom throw to be active, we just keep all the transistors off, and this diode is going to conduct that current. And if you want the bottom throw to be active, we just turn that bottom transistor on, and that's how the current is going to flow. So this is for the negative cases. All right, so it can handle throw currents that are, pole currents that are positive and negative, but at the same time, the throw voltage is always positive. All right. An example for this could be, for instance, a bidirectional buck converter. Okay. And so let me draw the bidirectional buck, and by the way, this could be redrawn. Let me just redraw it as this. All right, so probably have seen this before.
It's called the half bridge, right?
Yeah, you could call it. This is like a half bridge kind of a cell. So sometimes when you buy a pack, you can actually buying all of these 4 devices together. And now you can see that. Why is it that if a lot of times we have a MOSFET and there is this body diode of the MOSFET in parallel with that, it's not necessarily a bad thing, because in a lot of applications, when your current is bidirectional, you can actually use that diode if you choose to use it. So this particular switch is called the right half-plane switch. Okay? Or a 2-quadrant switch. And as I said, a good example for a right half-plane switch is the bidirectional buck converter. All right, so if you look at the bidirectional buck, let's say we have 2 batteries, and some of them, sometimes the left-hand side battery is charging the left-hand side, and sometimes the other way around. So you have a converter like this. So sometimes the charge is flowing from left to right, sometimes it's flowing from right to left. So therefore, this current could be bidirectional. So if you want to realize this system, you can actually use this switch realization over here. Okay? Do we have an application where we have 2 batteries and sometimes one of them wants to charge the other? Anyone? a semi-application could be a hybrid vehicle, like you have a high voltage battery, you also have a low voltage battery. The high voltage battery is providing power to the traction motor, the low voltage battery is providing power to the auxiliary loads. So you have two batteries there, and sometimes the top one wants to charge the other, and sometimes the other way around. So a good example could be like that, or sometimes even a fuel cell, auxiliary loads for fuel cells. So bidirectional buck is nothing but a right half plane zero base, a right half plane switch, single pole double throw switch. What about a left half plane switch?
Is this also can be used as in regenerative braking when?
You could say that actually. In that case, you're right. You're right. Actually, for regen braking, you're actually looking at the same schematic. In that case, you don't have a battery on one side. You have a device that is sometimes consuming power, which is like an electric motor, and sometimes it is generating power, which is a generator. Yeah, good point. Yeah, you can exactly do the same thing. What about left half plane switch? So technically, now what we got to do is actually take this switch, which is the second quadrant switch, and put all of the components in parallel with the third quadrant switch. So in that case, this is going to be the realization for your left half plane switch. Oh, there's nothing connected here. Okay, so if the pole current is positive and you want the top throw to be the conductor of current, then you got to do nothing basically. You keep both of the transistors off, and the current is going to flow through the top diode. Now, if you want the bottom throw to be engaged, all you got to do is just turn on the bottom transistor, and in that case, the current is going to flow through this transistor. All right? And if your current is negative and you want the bottom throw to be engaged, you got to do nothing. Basically, the diode is going to automatically do that. So keep all the transistors off. And if you want the top basically throw to be active, you got to turn on this transistor. So the current is going to flow through the transistor. So you can actually, having a positive throw voltage, you can actually manipulate the positive and negative polarities or directions for the current, and having the top throw or the bottom throw to be engaged. All right. Any questions so far? Okay. Now, so what we did was we combined the first quadrant and the fourth quadrant switch to get a right half plane switch. And then we combine the second and third quadrants to get a left half plane switch. But sometimes the current is unidirectional, but the voltage is bidirectional, for instance, in a rectifier application. So sometimes we have to combine, the voltage is bidirectional, like an AC voltage, but then the current is always positive. For instance, you have an AC source and you're supplying power to a resistive load or something like that. So in that case, we are looking at a top half plane switch. So we have to combine the first and the second quadrants. All right, so let's take a look at that.
Dr. Ferdowsi?
Yes.
So when we parallel the components of the third and the fourth quadrant,
Okay.
we have transistors at the bottom legs for both of them.
You said the third and the fourth quadrant? Or the second and third?
I'm sorry, second
and third. Okay.
Okay, second and third. I'm sorry. I got confused.
Okay. So you got the answer?
Yeah.
Okay, good. So technically we are putting this diode in parallel with this transistor down here, and this transistor in parallel with this diode over here. So this was second. So let me say, so this is like second plus third. And this is first plus fourth. All right. Now we are trying to combine first and second. And remember, in this case, voltage is bipolar, but the current is positive. So instead of, so you have to put actually elements in series with each other. So let me draw it. It's going to make much more sense after I draw it. So let me see. Okay. Okay, so we get a structure like this, and in this case, the throw voltage can be positive or negative. So for instance, let's consider a case that the throw voltage is positive. As long as the current is concerned, if you turn the top transistor on, the top throw will be conducting the positive current. And if you turn the bottom transistor on, the bottom transistor, and obviously we shouldn't turn both of them on. But as long as blocking the voltage is concerned, let's say we have a like 100 volts over here. Okay? And if this transistor is turned on, so in that case, this diode is actually blocking that voltage. So no problem there. Or if the bottom transistor is on, then this switch that is off is going to block that 100 volts. So no problem there. If the voltage is negative, in this polarity, all right, so let's say the top throw is engaged, and in that case, we have 100 volts appearing here. So the transistor, the bottom transistor is actually blocking the voltage. If the bottom throw is engaged, then we have this diode reverse biased. So it's actually blocking that negative voltage. So no matter where we are, there is at least one component that is blocking the negative or positive voltage, so we don't have to worry about, things getting out of hand. All right, and I'm going to have an example for this later. So this is when you have basically, this called a top half plane. And it is still a 2-quadrant switch. Okay, and this is basically a combination of the first quadrant plus the second quadrant. All right. Now, what if the pole current is negative, which gives us to the bottom half plane switch? So technically now we are combining the third quadrant and the fourth quadrant. So as you can see, compared to the top half plane switch, all we did was we kind of flipped it basically, and technically, and the negative current will be supported. If this transistor on, the current will flow here. If the bottom transistor is on, the current is going to flow down there. So we are looking at C and 1 minus C as commands to these two transistors. So no problem there. In terms of blocking positive voltages, if we have a conduction going on over here or the transistor is on, that positive voltage is being blocked by this diode basically. Okay? And I'm sorry, it's being blocked by this transistor. All right, and if the voltage is negative, that negative voltage is going to be blocked by this diode. So if the top throw is active, doesn't matter if the voltage is positive or negative, one of these elements is going to block that. And in case we have current going through the bottom throw, or the bottom throw is basically shorted, and the voltage is positive, then the diode is blocking the voltage. If it is negative, then the transistor is blocking the voltage. Again, we have two elements kind of back to back. Doesn't matter what the polarity of the voltage is, it's actually gonna be able to block that voltage. So as I said, these structures are mainly used in rectifiers, and I'm gonna explain the rectifiers in a few minutes. Just bear with me. And before we get to the rectifiers, the question is, do we need sometimes a switch that is covering the entire plane, so all of the quadrants basically together? Or technically a 4-quadrant switch, okay? Do we have a 4-quadrant switch? The answer is yes. What we got to do is either combine the right half plane with the left half plane switches, or combine the top half plane with the bottom half plane switches to actually be able to get a 4-quadrant switch. A 4-quadrant switch is a switch that can handle positive and negative voltages, as well as left-hand side or left to right or right to left currents. So let me draw it over here. Like in, for instance, a matrix converter or something like this. So the pole current could be positive, it could be negative. And the throw voltage could be positive and it could be negative. All right? So there are 3 ways of realizing this switch, and looks like 2 of them are going to be identical. Let me draw them first and then explain them. So if you combine the top half, the right half plane and left half plane, it is going to get something like this. Oops, this is not supposed to look like this. Alright, so this is going to be just one of your throw switches, and these could be turned on together, it doesn't matter. Okay, so this is what we have, and these commands are 1 minus C. Okay, so what I have done here is I am trying to combine the right half plane and the left half plane. So I'm actually getting this element over here and then putting it in series with this guy. And then I'm getting this element over here and then putting it in series with this guy. So I put them in series to be able to basically handle any direction of the current and any polarity for the voltage. And by the way, this VT should hold on, Control Z. All right, let me just do one more thing. This should be negative. Okay. So that's what I did. Okay, so this is basically right half plane combined with left half plane. All right. So let's look at a couple of scenarios. For instance, let's look at one scenario where the pole current is positive and we want the top throw to be engaged. So basically what happens is we turn this transistor on and we turn this diode on, and there you go. They're actually conducting, no problem there. And then, for instance, if throw voltage is positive, then this diode is blocking the voltage, and no problem there. So the bottom throw is okay. The bottom throw is off, but we've got to make sure it can handle positive voltages. And let's look at another case. For instance, I don't know, let's pick red. For instance, let's consider I pole is negative and we want the bottom throw to be active. So basically this current is negative. We turn this transistor on and then the current is going to go through this diode. It doesn't matter if I turn the second transistor on or off, the diode is actually going to be conducting anyway. And if the throw voltage is positive, for instance, then this diode is going to be blocking the voltage. If it is negative, the other diode is going to be blocking the voltage. All right? So this is how you can manipulate in a way that your currents could be positive or negative, your voltages could be positive or negative, and you can always manage to have the top throw or the bottom throw active, conducting or not conducting the current. All right. Yes.
So is C the command, like would it just be 0 or 1, or is it the duty ratio?
Say that again.
C
is the command, okay.
And would C only be the control parameter, or would we use more than like one control parameter, like C dash maybe, or just?
You could consider C the control parameter, meaning that by definition, if C is 1, then you would like to see your current to flow. So this is how we define C. If C is 1, you would like the top throw to be shorted and to be conducting the current, basically. So that's the definition of C. So that's why we are kind of cautious about, is it C or 1 minus C? Like here, if C is 1, that means we have a conduction path over here. So no problem. If C is 0, that means the bottom throw should be active. That means we have a conduction path for the bottom one, something like that. Okay. So this is if you combine the right half plane with the left half plane. Another option would be combining these two guys, the top half plane with the bottom half plane, and that would be easy, just putting things in parallel. So basically what you can do is you can take this component and put it in parallel with here, and you can take this component and put it in parallel with this one. Again, you can realize a 4-quadrant switch. All right, so let's do that. And as it turns out, it's pretty much similar to what we already have on the screen. So now I am trying to combine, let me write it over here first. I'm trying to combine top half plane with the bottom half plane. All right, so I'm going to draw it. All right. And for the top throw, we almost have a similar thing. And these two are basically the same. They're just drawn differently. Let me just see if I can make it a little bit smaller. These two switches are basically the same. You can actually, for instance, if you swap the position of these two components, then provide a parallel, conduction or connection path over here, you're going to end up with what we already had, basically, which was a combination of the right half plane and the left half plane. But the bottom one is a little bit easier to understand. For instance, if your current is positive, this will be the conduction. If it is negative, this will be the conduction for the top throw to be engaged, and things like that. So it's a little bit easier to imagine, but it's basically the very same exact thing. All right, so one last switch realization, which is another 4-quadrant switch, but still a bit different from these two guys. As you can see over here, we are using 4 switches and 4 diodes. And each switch needs to have a gate driver, so we need to have also 4 gate drivers, or at least 2 gate drivers. Then you realize that it is not going to be very cost effective. So there is another way of realizing this switch, which is a little bit different. So this is how it looks like. So here we are using more diodes, but less number of switches. All right. And almost the same thing is replicated down here. So the advantage here is we are actually saving on the number of switches, because switches are controlled, you need gate drivers, but diodes are not controlled, so you don't really need a gate driver for them. Okay, so for instance, if we want, let's consider a scenario where the pole current is positive and we want the top switch to be the top throw to be engaged. So we just turn the top switch on and the current is going to flow like this. All right. If still we want the top throw to be conducting with a negative pole current, again we got to just turn that top transistor on, and this is how the current is going to flow. All right, something like that. And a similar way, if you need conduction in the bottom throw, basically. All right, so we have almost 2 different ways of realizing a 4-quadrant switch. Any questions? So we kind of had some examples already for the first quadrant single pole double throw switch, which was like the buck converter and the boost converter and things like that. Let's take a look at some examples for like a top half plane or a bottom half plane kind of a switch. Okay?
Dr. Ferdowsi?
Yes.
If just, can we have like current flow, like just the top row is conducting and the bottom row is totally out of picture and vice versa?
For what? Which particular? For this last one?
Yeah, for this last one. So could we have just that VT applied, but the bottom throw is not in the picture, or without that? I mean. So
okay. So the question is, the current is positive or negative, or?
Yeah, positive or negative, but just the top throw is conducting and the bottom throw is not conducting, or vice versa. Is it possible?
Yeah. So technically, if you command this transistor to be on, as we saw right now, you can support positive and negative currents over here. So the top throw is engaged. It is conducting any polarity of current that you want, and only the top throw is engaged. The bottom throw is not engaged. And if you command the bottom transistor to be on, then you can have positive current conduction and negative current conduction over here. So the top throw is not engaged, and you can have positive or negative currents basically flowing through the throw.
With this configuration, you have an extra diode voltage drop, though, compared to the other two configurations?
That's right. So you're right. So basically, in terms of losses, you may argue that I have a voltage drop here, I have an extra voltage drop over here compared to the previous case. So that's right. So, but sometimes your voltage is too high. Again, depends on the application. You may argue that that doesn't exist here, but sometimes your voltage is too high that two of these devices cannot handle that high voltage. You need to have like 3 devices or something like that. But you're right. In terms of losses, this is not very effective. We had a question, yes?
If we want to add RHP and LHP in parallel, not in series, does that work?
Okay, R right half plane, and if you want to combine this and this,
yes,
put them in series,
parallel.
put them in parallel. You should not put them in parallel, because what you get is something like this. Let me draw that. So you already have this. And then you put it in parallel with this. Right? Is that a question?
Yes.
All right. So as you can see, this diode, I mean, this way we don't really have any control over this device. It is going to conduct bidirectional current. So, for instance, if your current is in this direction, this diode is going to conduct. If it is in the other direction, it's going to conduct like this. But we don't have any control in terms of turning it on or off. It's going to make its own decisions. So it is going to work, but the transistors are not going to play any role, basically. Other questions? Okay. So let's have an example for a rectifier. In a rectifier, most of the time we are looking at a source that is AC and a load that is relatively DC. So we are looking at a terminal or a throw voltage that is positive and negative, but at the same time, your pole current is basically positive. So let's take a look here. So example for let me see what it was called. So for instance, an example for a top half plane switch. Okay, so I'm going to draw it. So this is the secondary side of the transformer, and I have a primary side. So I have an AC voltage here. Okay, I'm kind of splitting the voltage, and then actually, you can argue that we don't really need this capacitor. It depends. I mean, this L and C are basically your low pass, your filter. And you can argue that you may or may not need the capacitor depending on the application. So I'm just going to draw it in dotted lines. and then this is connected to this middle point. All right. So for instance, this is like an electric motor or something like this, like a DC machine. So this current is positive. And the throw voltage, because it's being fed by the AC system, is sometimes positive, it is sometimes negative. So what you can do with this converter, again, you can see there is only one single pole double throw switch. There is a filtering mechanism, like the inductor and the capacitor. In this particular case, like in a buck converter, the L and C were trying to give you the DC component of the signal and eliminate all of the ripple. Over here, they are trying to give you the fundamental component and then eliminate all the other components. I'm sorry, this is a rectifier, so still they are trying to give you a DC component. So technically, how it works is, for instance, if this is your AC signal, then if you measure the voltage from here to here, let me call it Vx, so this is like Vn. All right, so Vx would look like this. Or something like this. So if you want Vx to follow Vn, we gotta, if you are in the positive, basically half cycle, we gotta turn like this transistor on. Okay, whenever we turn this transistor on, Vx and Vn are the same. So if you are in the positive, for instance, cycle, that would make sense. If we want Vx to be opposing Vn, then we have to turn the bottom transistor on. So, and that is actually like here we have S2 on. Okay. By applying this trick, we are basically applying part of the signal, the input signal, to the output. You can see the signal has a major DC component. So if you have a low-pass filter, you can actually obtain the DC component, and you can call it a rectifier. So basically, using a single pole double throw switch, you can build a rectifier. Another example, instead of using a center tapped inductor, you can use two of these basically single pole double throw switches to build the same thing. So instead of using a center tapped transformer, you can use this circuit, kind of an H-bridge. So this is the classic trick in power electronics. If you want to use half a bridge, either you have to split your voltage using two equal capacitors or a center tapped transformers like we did earlier. But now, instead of using that, you're using a full bridge. So you have S1 and then S2 complementing each other, then S3 and S4 complementing each other. And this is, for instance, your output voltage. All right, so same scenario is going on. For instance, let me just redraw this. This is your input voltage. This is the opposite of your input voltage. And depending on your switch configuration, you can follow whatever you want. And then again here we have a signal which is like Vx from here to here, for instance, which is relatively DC. All you got to do is just apply it to a low-pass filter to give you a relatively DC signal. And again, this is assuming that this inductor is large enough, so this current is always positive. So in terms of commands that are applied to the switches, here we have S1 and S4 on. So if S1 and S4 are on, Vx and Vin are the same. Vx is just following Vin. So because we have a short circuit here, and we have a short circuit basically here. Otherwise, we have to turn S2 and S3 on. So in that case, this switch is on, this switch is on. It's like our input and output are equal with the negative polarity involved. So technically we are following negative Vn. So this is Vn, and this is negative Vn. So by this manipulation, you can always cut out part of the voltage from the input, the positive value of the input and the negative value of the input. Actually, on average, you can actually apply a positive voltage to your load. So this was an example of a top half-plane switch, which could be used in a rectifier application. Okay? Any questions? Or I feel like I have one more example. Yes.
Why is the Vx negative in the initial part of the second half cycle?
Oh, because it is following. Oh, you mean this? Okay. So the question is, why is Vx negative in this area?
Yep.
So remember, whenever S1 and S4 are on, whenever S1 is on and S4 is on, this point is shorted here, and this point is shorted here. So Vx is Vn. In that segment of time, Vn is negative. So Vx is following the negative value of Vn basically.
But in that case, the diodes will be reverse biased, right?
In that case, the diode would be reverse biased. No. Don't think about it like that. Because just the input voltage is negative, the diodes are not going to be reverse biased. So let me simplify this in this way. So the argument is, if our input voltage is negative, like this, and we have a transistor that is turned on here, so this is on, okay, what happens to the diode? And remember, this current is positive, and it is going to push this diode to turn on anyway. All right, so this diode is not turning on and off depending on the polarity of your input voltage. This diode is turned on because the inductor is pushing it to turn on. However, that negative voltage that you are concerned about is appearing here. So this bottom transistor is actually blocking the voltage. All of the diodes are trying to actually conduct. I mean, because even if you look at this voltage over here, it is agreeing with the polarity that the diode would actually start conducting. But there is no possibility for this to be on because this transistor in the bottom is off. So, for instance, if we have, I don't know, negative 20 volts, let me just write it 20 volts here, that 20 volts appears here. Okay? The rest of the components, if you measure them, they're almost zero, for instance. Okay?
We can send the power to the other side.
We can send the power to the other side. You mean the right-hand side?
From the load to the source.
In this case, you're right. In this case, you are kind of charging your source. You're right. Temporarily, you're charging your source. Or sending power back to your source, basically. So this diode, so please do not make this mistake. This diode does not turn on and off based on this voltage. It turns on and off based on the current of the inductor. If the current of the inductor is in a direction that is pushing the diode to turn on, then the diode is going to turn on. All right, very good question.
Excuse me.
Yes.
Does the diode capability can handle the current if it's like?
Oh, the question is, can this diode handle the current? So that depends on your design. I mean, what is the value of this current? What is the average value of this current? Then you have to pick a diode that can handle that amount of current. It depends on your power rating, basically. Is that the question? Okay, so one last example. So we looked at DC-DC converters. They are usually using single quadrant switches. We looked at rectifiers that they are using 2 quadrant switches. Now let's look at inverters and see how those switches are realized. In an inverter, basically, your source is a DC source. You're expecting your throw voltage to be positive, but then the output voltage and the output current are sinusoidal. So basically, they are both positive and negative. So in these switches, if you look, so we are looking, for instance, at a right half-plane switch, because then the throw voltage, which is your DC source, is positive, then the pole current is positive or negative. So the same thing that we use for a bidirectional boost, we can use the exact same thing for an inverter. So for instance, we are looking at an example where the throw voltage is positive, and at the same time the pole current is bidirectional. So we're looking at the right half plane switch, and an example would be an inverter. All right, so I'm going to draw it and actually show you how we can use this switch realization that we just studied. Oops, too much. Okay. So I'm using this the right half plane switch because input voltage is DC, it's always positive, but the output current is bidirectional. So again, I'm drawing this capacitor, but you can argue that we may not need this capacitor. All right, so this is an inverter, like a half-bridge inverter. Now again, the trick is whenever you are using a half-bridge, structure, you have to split your input voltage. What I did previously when I was using this half bridge, I had to split my input voltage. Oops, too much. When I was using this half bridge structure, I had to split my input voltage using a center tap transformer. Here, life is a little bit easier. First of all, I cannot use a transformer here because my source is a DC source. And the thing is, because this is an inverter, this current is an AC current. So when you're splitting a voltage, a DC voltage using two capacitors, you got to make sure that the current that is going into these two caps on average should be 0. Otherwise, one of these capacitors is going to get charged and the other one is going to keep getting discharged and it's not going to split anymore. So this is VDC over 2. Again, these capacitors are assumed to be large enough, so their voltages do not really change much. They are equal in terms of value or size, so that means they are kind of splitting the input voltage. So one more time, if you look at this current and this voltage, so throw voltage is positive, but this current could be positive or negative because it's an inverter. It's like, let's say, for instance, this is exponential or sinusoidal signal or whatever it is, and the output voltage is also AC. And this is also an AC current. All right. So now what you can do is, if you turn the top transistor on, you are applying the top capacitor voltage to your Vx. If you turn the bottom transistor on, you're applying the voltage of the bottom transistor or the bottom capacitor to Vx with a negative polarity. So this way, Vx could be a square-shaped kind of a signal. So let me just draw it over here. And S1 is kind of complementing S2. So it's being turned on and off symmetrically, like 180 degrees on, 180 degrees off. And then if S1 is on, Vx is the voltage of the top capacitor, which is VDC over 2. And if S1 is off, in other words, S2 is on, Vx is the opposite of the capacitor, the second capacitor, the opposite of this voltage down here, which is again negative VDC over 2. So by this very simple trick, we can actually generate a Vx signal that is kind of AC, basically. It's a square-shaped AC. It's not sinusoidal AC. But then you have a filter, an inductor, and maybe a capacitor over here to give you the fundamental harmonic of this AC or a square-shaped AC signal, which is, for instance, a sinusoidal signal. Any questions? Yes?
Does the output takes like exponential growth and decades with?
Okay, it may or may not. It depends on the value of your inductor and the value of your capacitor. Actually, if you ever use a capacitor or not. If I do not use a capacitor and my inductor is, for instance, relatively small, or the time constant is relatively small, your current is going to look like this. Okay, this is a small. Your time constant is small. If your time constant is large, then you are going to see almost a triangular. So this goes all back to what's the value of your load, what's the value of your inductor. In other words, what are the parameters of your filter, basically. What are the components that you are filtering and what are the components that you are not filtering. If you are not happy with either one of these, so these are all IL. Are you happy with this or not? Did you really want to have exactly a sinusoidal signal? That means your filter is not good enough. You have to use a higher order filter, for instance, add a capacitor or something like that. So in power electronics, if you see, usually you have a source, you have a load. Usually you draw the source on the left-hand side, you draw the load on the right-hand side. Between them, there is a switching configuration, and then you have to figure out what that switching configuration should be in terms of, is the throw voltage positive, or is it negative, or is it sometimes positive, sometimes negative? Is my pole current positive or negative, or it's sometimes bidirectional, basically? And then there is a filtering going on as well. Sometimes this filter is trying to give you the DC component of your signal, like in a buck converter. We exactly use an ln and c, and then they are supposed to give you the DC component of Vx, which is a square-shaped signal. Sometimes they are trying to, for instance, eliminate some higher order harmonics, like over here we are using L and maybe sometimes C to eliminate the higher order harmonics in your Vx waveform. So we are trying to get away from a square-shaped waveform and get closer to a sinusoidal waveform. All right, the next topic that I was going to talk about was the Fourier series, analysis of converters, but we don't have enough time. It's only 4 minutes left. So I'm going to stop here, and I'm going to see you guys on Thursday. If you have a question, what's the question?
Can we apply here the pulse width modulation?
Can we apply here what?
Pulse width modulation.
Pulse width modulation here, you cannot, for this particular one, you cannot. You can and you cannot. I mean, in this case, so the very essential trick over here is your duty cycle is 180 degrees. If you deviate from this 180 degree duty cycle, then you are going to have a DC component over here. And that DC component is going to charge and discharge the capacitors in a way that you don't want to happen. So you can do a little bit of a PWM, go a little bit lower or a little bit higher. But on average, you should always be at 180 degrees. Otherwise, you are constantly charging or discharging one of the capacitors. All right, so I'll see you guys on Thursday. And please note that there is a sign-up sheet circulating. All right, see you guys later.